Welcome to the Walton Pi. Today we're going to be talking about modeling with functions. This is my 8th video in my AP Precalculus course where I am going to cover all the topics that show up on the AP Precalculus exam. So one of the big reasons that mathematics is so powerful is it's used to model the real world. For example, Galileo, he measured the time that it took a bunch of different cannonballs to fall from various heights, and then he developed a model to describe the behavior he saw. He discovered that the time that it took for the cannonballs to fall, we're going to call that t, and the height that he dropped it from, h, is going to be t squared is h divided by 4.9. This is just a model of the real world. The time, seconds, t squared, that's how long it takes for the cannonball to fall, and then the height in meters from its dropped. It's just measuring those different things and showing the relationship between those two measurements. Now, when we're developing these models, which we're going to be doing a lot of in this course, we have to be aware that they only apply in certain circumstances. So in Galileo's cannonball model, the model is only applying for t values bigger than 0. It's not measuring the height of the cannonball before you drop it. It's only measuring it after you've dropped it. It also isn't going to apply for values after the balls hit the ground. Like once it hits the ground, it's not moving anymore, so the height and the time are going to stop changing, and so that's another restriction that we have to place on our model. And so every single model that you're going to come across is going to come with assumptions and restrictions of where they can or cannot be used. So when we construct a model, we're always going to have underlying assumptions about what's consistent in the model and how different quantities can change together. Because of that, we're going to often require domain or range restrictions depending on the context of the problem. We're going to need to also look at the extreme values of the dataset. That might impact the domain or range restrictions we have to pick. And sometimes we might even have to choose what makes sense mathematically. For example, with the cannonball problem, we had to restrict the domain because not all the values of t were going to make sense. And then once a model has been made, it can then be used to draw conclusions about the modeled data and behavior. So, different types of functions are going to model different real-world behaviors. Linear functions are going to be best when our data sets or our behaviors have roughly constant rates of change. For example, a linear model would be best used on a data set comparing miles driven with gasoline consumed. Here, our roughly constant rate of change is the fuel efficiency in miles per gallon. It's not a perfect constant rate of change, but it's going to be approximately constant, and so that's why this would probably be the best model for this situation. Now, quadratic functions, those are going to be used to model behaviors or data sets whose rates of change are roughly linear themselves. For example, a quadratic model is going to be used on Galileo's dataset comparing the distance a cannonball fell with the time that passed. Here, our roughly linear rate of change is tracking the velocity of the ball, which is going to be increasing linearly. Now, a common structure that can indicate that a quadratic function should probably be used is when the dataset's roughly symmetric and there's a unique maximum or minimum. That sort of graph or rough shape looks roughly quadratic, and so it's likely that you could get a quadratic function to model it fairly accurately. Another instance that quadratic functions would often be used are if there's two dimensions or areas involved. Those are going to naturally have x squareds come up in them, and so it's likely going to be a quadratic that's going to be involved there. And then if we're looking at 3 dimensions or volumes, we're often going to have cubic functions model that behavior because we're going to have x cubes show up very frequently in that type of behavior. Now, if your data set has multiple zeros or multiple minima and maxima, then we're likely going to be having a polynomial as our modeling function. Not a line because that would only have one zero, but we're going to probably have a polynomial. And when we're writing a polynomial, be a little bit careful about overfitting because if you have n data points, it can be modeled perfectly with an n plus 1 degree polynomial. Okay, so if the degree of your function is close to the number of data points that you have, you're overfitting your model. It's like, yes, your function is matching all the points, but it's not being a good model because it's matching them too perfectly. You need to account for the fact that there's going to be error in your measurements, and so that means that you're probably overfitting your model. If the function's degree is getting close to the number of data points, you're probably matching the data too closely for it to be a good model. So this means that if you have n plus 1 points, use a polynomial of degree n or less. I recommend trying to use one that's significantly smaller degree than the number of points you have. Furthermore, if your data has n non-trivially distinct inputs with roughly constant output, then it's likely that the modeling function is a polynomial of degree n. So for example, let's look at this graph, or this set of data points. Okay, if we look here, we have 3 data points that are all roughly the same constant output. They each have an output of roughly 2. And we have 3 of those points, so we're likely going to have a function of degree 3 that will track this behavior. And if we look at this graph, which tracks the behavior pretty well, that is a cubic polynomial. It is a degree 3 polynomial. Now, how did I get this function? Well, we have x plus 2 as one of the factors of the polynomial. X plus 2, that is one of the points that we know. We know there is a point at x equals negative 2, positive 2. And so x plus 2 means that we should have a 0 at negative 2. Now, because the y value is not 0 but is instead 2, that's why there's a plus 2 at the very end. So we have x plus 2 giving us the first point that's there. X minus 0.5 gives us our second point, and x minus 2.5 gives us our third point. And then the 2/5 is just so that the vertical stretch is roughly the same as what we are observing. And so this function is a pretty good model for this data set. If your data set has vastly different behavior in different intervals, then you're probably going to be needing to use a piecewise function to model the behavior. Now remember, a piecewise function is a function defined differently on non-overlapping intervals. For example, if this is our graph of our function, the piecewise function is this. F of x is 3 when x is less than or equal to 0, x squared when x is between 0 and 2, and 6 minus x when 2 is less than x. The definition of piecewise means that the intervals need to not overlap. However, oftentimes if they do overlap and would have the same value at both points, such as x squared and 6 minus x, they both agree at x equals 2. Oftentimes you might see it as including the overlap, but that's just signifying, hey, these are having the same output at this point. But the convention is in fact going to be like this, where you don't have overlap in your definition of your intervals. Okay, if you're trying to figure out how to graph this on Desmos, the very bottom line, that would be what you would type into Desmos to try and get this exact graph. So go ahead and play with that to figure out how to graph piecewise functions on Desmos. Now, if your data set or scenario involves quantities that are inversely related, such as gravitational pull, that gets stronger the closer you are and weaker the farther apart you are, that is going to be something that is inversely related. That is likely going to be modeled with a rational function. So for example, the gravitational pull, little g, is the mass of the first object, big M, times the mass of the second object, little m, times big G, the gravitational constant, divided by r squared, the distance between the center of masses of those objects. That tells us what the gravitational pull between those two objects is. And this is an inverse relationship. R is our variable, big M, little m, and big G, all of those are constants. We have a rational function here. How do we construct different models? This is going to be one of those things that just takes a lot of practice. Every single problem is going to be unique, but we can often construct them by carefully reading the scenario and looking for clues in the context. So if a function for a similar scenario has been provided, you could use function transformations to create a new model. If you're given a data set, you can use technology to find the appropriate linear regression, quadratic regression, cubic regression, quartic regression. All of these are things that calculators can be able to do and help you figure out. And then if you have a piecewise scenario, you're just going to have to repeat this process on each independent interval. Now, I hope this video was helpful in understanding how we can do modeling behaviors. There's going to be more videos on this for exponential functions, but this is the conclusion of the first unit in the AP Precalculus course. If this has been helpful, please like and subscribe. It really helps me out. And please share this with other friends who are taking AP Precalculus. It really helps me out to keep making these videos. I hope you have a great rest of your day, and good luck with all of your math.